Today we will be discussing about Compton effect, pair production, and the uncertainty principle. So we start with the Compton effect. So Compton observed that when a gamma ray photon is incident on a slab of matter, the light is scattered is having different wavelength than that of the incident photon. The wavelength of the scattered photon is greater than the wavelength of the incident photon. You can see in this figure, a gamma rays photon is coming. It is getting scattered and an electron is also emitted. In both the diagrams, you can see this. The wavelength of, as I said, the wavelength of the scattered photon is greater than the wavelength of the incident photon. Lambda is the wavelength of the incident photon and lambda dash is the wavelength of the scattered photon. So this quantity is equal to, this change in wavelength is equal to h upon mc into 1 minus cos phi, where phi is the angle of the scattering. So the basic physics behind this is that when a photon collides with an electron, it transfers some of its energy to the electron so that electron can escape from its orbit and go. So this transfers of energy, after this transfer of energy, the photon is energy reduces. As the wavelength is inversely proportional to the energy, so when I said that the photon energy reduces, that means the wavelength increases. So the wavelength of the scattered photon is greater than the wavelength of the incident photon. In elastic collisions, both momentum and energy are conserved, like you can see. The reverse of this is that when a gamma ray of sufficiently short wavelength are fired into a metal plate, they are converted into an electron and a positron. So when a gamma ray photon is incident, there are two particles produced. One is an electron and the other is a positron, that is an antiparticle of the electron. You can see in the figure, gamma ray photon is coming and a pair of particles constituting an electron and a positron, each of having mass m and rest energy mc square. So the photon wavelength for this to happen must be short, that the photon energy is at least 2 mc square. If it is not less than 2 mc square, then two particles with mc square can't be emitted from the slab. And for the particles to have this exactly the same energy and angle in order to conserve the momentum. The reverse process can also occur and a positron and an electron can come together to annihilate and produce a photon or more than one photon. So we have three processes with us. In our previous lecture, we discussed about the photoelectric effect. When a gamma ray photon strikes, a photoelectron is emitted. The Compton effect, when a gamma ray photon strikes, incident for gamma ray photon is scattered and an electron is also emitted and the wavelength of the scattered light is greater than the wavelength of the incident light. In photoelectric effect, only the electron was emitted and the incident photon was absorbed. In the Compton scattering, the photon is scattered, it is not absorbed, and it is scattered, and the electron is also emitted. And in pair production, the gamma ray photon after striking results in the emission of an electron and a positron. Now we come to uncertainty. So when a photon passes through a narrow slit, its momentum becomes uncertain and the photon can be deflected on the either side. So if we limit the vertical spaces of the slit, that is the width of the slit, the momentum becomes uncertain. And Heisenberg gave a principle that the momentum and the position can't be measured simultaneously. We have to measure in terms of uncertainty. But you will certainly ask that when the position and momentum are uncertain, then why we get a regular diffraction pattern? So the reason behind that is not a single photon, but numerous photons strike the screen. And the uncertainty I am talking is in terms of a single photon. The diffraction pattern that we get will be possible even if a single photon is present at the time of experiment. The pattern is not a consequence of the interference between the two photons. Each photon interferes with itself. So in 1927, Heisenberg postulated that it is impossible to specify simultaneously the arbitrary precision, both momentum and position of a particle. Later, another pair was also introduced that the energy and time also cannot be measured simultaneously. So the consequence of the uncertainty principle is that if we cannot, for example, determine the exact position of a photon, so in our classical mechanics, we were talking in terms of the exact position and momentum of a particle. But in quantum mechanics, we are talking in terms of uncertainties and probability. We are openly saying that the position and momentum can't be determined simultaneously. We will be measuring them in terms of uncertainty and probability. So this is about this Compton effect, and we will start with the quantum mechanics in our next lecture. So thanks